All right, are you coffeeed up? Ready to go for diagnostics? Okay, so let's do this. Let's talk about ex situ diagnostics. Woo, I moved it. So this part is mostly about sampling and all the artifacts associated with sampling and how we might be able to get around the artifacts. Okay, let's see if maybe I have connection. Okay, let me try this again. Okay, I'm going to see if I can. Yes, we're back. Okay. Yeah. Okay. So, yeah, let's just get going. Oh, yeah, we're into diagnostics, and then tomorrow we'll talk about atmospheric. We'll probably finish diagnostics tomorrow and then we'll talk about atmospheric. Okay, so you want to make measurements. You want to make a whole bunch of you want to know different properties of the particles. And how you do your measurements, what will depend on what you actually want to measure, right? So there are a whole bunch of different parameters you might want to understand about your particles, or maybe you don't care about some of these parameters, and then you can be a little bit more flexible about how you want to sample your particles. And it's not just sampling, it's sampling and storing, or putting, like if you have a highly volatile particle, for instance, it's going to be hard to do a technique that requires you have vacuum, right? Because you'll just vaporize your particles. So you have to think carefully about how you're going to do these measurements. Then you want to probably do, if you're trying, like say you're trying to model soot formation, you're going to want to also know, and you're trying to compare to data, you're going to want to also know all these other parameters associated with the measurement. Temperature for chemistry is hugely important. It's exponential with temperature, right? So you want to know temperature, and you probably want to know, like, if you're under different pressure conditions, if your burner you probably want to know your burner temperature. There are all these different parameters that we usually need to think about. So we'll talk a little bit about some of that as well. Okay, so let's start with some of the techniques that we've already talked about, just how these measurements were made and how you might want to make them. Okay, so here's a sampling. We talked about this measurement, the photoionization, mass spectrometry on the full particles that the Grothier, et al. Did. And remember, this is the one with the two modes, and we're trying to figure out, if those two modes were different in character or not. So the way they sample from a flame, you see that they have a quartz probe. So it's like just like an eyedropper almost that goes into their premixed flame. And often when people do this type of measurement, they have the quartz probe is sitting above the burner. You don't usually do metal because it'll melt. Quartz will go to higher temperature, and it's not highly reactive. So you're sitting there with your quartz probe, and you move the burner up and down so you can get different heights in the burner. So in this case, they extracted this whole thing into a vacuum chamber, and they basically made a type of beam. This is the beam of all the gas, like all the particles, like straight into, they basically shot this into their vacuum machine and then ionized with a laser and then did a mass spec. Okay, so The way they did their sampling, though, is if you notice at the top in that circle, at that red circle of their sampling, you see that, so their sampling goes right directly from the flame. They use helium to carry the particles over to their chamber, and then they take the whole thing, helium and particles, directly into the chamber. And how they did that was through what they call a skimmer. So all of that helium plus particles. So they do a dilution with helium. They cool with helium, not the best gas to cool with, but when you're doing a supersonic expansion, so they do a supersonic expansion through this, what you call that cone shape, people call a skimmer for molecular beams. You're mechanical engineers, most of you, right? So you know this technology. This makes a supersonic expansion into their machine. So that immediately cools their whole sample. So they do a dilution and a cooling into the machine, and then they do the mass spectrometry. So this is, so then they do photoionization. They don't vaporize in this machine. In this, this is transmission electron microscopy. So let me, instead of talking about actually how you do sampling right now, let's talk about some of these techniques. So that was how you got mass, they cooled their beam there and made a molecular beam of their small, of their molecules plus their small particles, and actually ionized the entire particle, so it didn't vaporize, right? Okay, so here's another way of making these small measurements of these small particles with sampling. So another ex situ technique. This is looked at this again earlier, right? Yesterday and earlier today. You basically take your sample, put it on a substrate. So the way they did these measurements is they took a substrate and they stuck it into the flame and pulled it out and then had their sample on this. And they do this really fast. You don't want to melt your grid. Is usually a carbon-coated gold often. So you do this really fast, like it's a fast inject. And we'll talk a little bit about this later. And then they do transmission electron microscopy. So you send an electron beam through your samples, but your sample is sitting on a grid, so the electron beam can go through and collect the electrons. You also can look at the electrons that are bounced off of the sample. So you have that's how you get your scanning. When you see people say scanning electron microscopy, you'll see, so that's that bounced like a beam, and the one that goes through is the transmission electron microscopy, right? So you see both types. The TEM is actually better for higher resolution, but if you have a big sample and you don't need any resolution better than a nanometer, a lot of people will use SEM, okay? Okay, so that's how they make that measurement. So this is a TEM of a particle. Oh yeah, this is a coated particle that collapsed. That's the restructuring. Here's how people do. So you can get aggregate size. So you can get that tiny particle size. But remember, it's hard to sample the real incipient particles. They're really the smallest particles. Remember, we weren't able to sample them. It's really hard to sample those really small particle sizes using just a TEM grid inserted into the flame. But it's really pretty easy to get these aggregates, okay? And for aggregates on the size of 100 or so nanometers, it's a really great technique, just to do regular TEM, put it into the machine. This is a new technique, an interesting technique where they do TEM tomography, where they're able to like rotate the sample and get a 3D image of their aggregate. This is really cool because a lot of times we're trying to understand the structure, the morphology of these aggregates when they're sitting on the grid, and you just get basically this image, like you're looking through like at what's ever fallen onto the grid. Sometimes you'll be able to see the little arms like moving a little bit in the TEM machine. But it's really hard to figure out what the three-dimensional structure is. But this is tomography. You don't see this very often. I think it's very computationally labor-intensive to get one of these images. But it's a really cool technique, and you can see how that aggregate is structured versus how it looks in the 2D TEM imaging. Okay. And this is SEM tomography, so you can do the same thing with SEM as well. Rotate your sample and get some structure. Okay, and then you can take these TEM machines and do high-resolution TEM. So this is a different machine where you do high-resolution TEM, where you actually get the fine structure of the particle. People have actually think they can see even how big these like graphene-like sheets are and calculate, they even calculate if it has a little bit of curvature, they can calculate how much curvature it has. So people have done some really, really beautiful work with these high-resolution TEM machines where you can get the fine structure of the particle. This is a technique that we get almost everything we know about, the disordered center and then the ordered shells on the outside. We know almost, this is the only technique that's been able to give us that kind of information. And this is the type of information, all of this came from high resolution TEM, okay? And then remember we were talking about atomic force microscopy, right? Where we could actually image the incipient particles and figure out that they were seemed to be squishing on the our substrate because if the particles were spherical, then we were seeing it like wider than it was tall. So AFM helped us actually see that these incipient particles seem to be somewhat waxy, or at least some or liquid-like maybe, but probably not, but pretty viscous if they're liquid-like, so kind of waxy type particles. That was all done with this AFM machine. And remember, I was telling you yesterday, the way this works is you have this tip that goes across, it's actually a mechanical type of mechanism. It's that you have this actual tip that goes across your sample. You drag across your sample, and when it hits something, the mirror on the top of the tip tilts a little bit, and your laser beam that's reflected off that mirror moves. So you can watch the movement of that laser beam and know when you have a deflection of your tip. It's a very clever technique. And you can do, so this is the TM, the AFM I was just talking about, where you could see the position of that tip and that particle smeared out. Okay. This is the high resolution version of it. Remember, we were it actually can see individual atoms. This is really interesting work, and this type of technique was invented at IBM in the 90s, and I think these people collaborated with people at IBM in, maybe it was in Switzerland, in Europe somewhere, to actually map out the structures of these pHs. So you actually can see individual carbon atoms. It's so cool. Okay, and then even see radicals. You can see the extra little signal from radicals. And then scanning tunneling microscopy is a way of looking at the electron density as you scan across the surface and look at the electron transmission as it goes across the sample. That's getting tunneling microscopy, because electrons are small enough that they can tunnel through materials, right? And you can see that gives you electron density. Okay, and then we have let's see, which one is this? Oh, helium ion microscopy, where you actually, instead of using electrons, you can use helium atoms. And that can give you information that's a little bit, different from TEM in that you're actually now sending a bigger particle now and slamming it into your sample, right? And then looking at it reflect. So its resolution isn't quite as good as electrons. Electrons are really, really useful at being able to sample materials and being able to interact with electron density. Now, once you start to get to bigger particles like a helium atom, you're not so much sampling electron density. You're sampling more like the nucleus, right? So, you're not so easily able to see the high resolution that you can get with electron. So this is helium ion microscopy. And this is, remember, that's the technique that we use to see these different structures, like that the particles actually may not be spherical. So, and it's the same burner, remember, the same conditions where with TEM, we saw the spherical particles. Okay. And we talked, I know some of you actually have been using these mobility type measurements. This is a scanning mobility particle sizer. So in this technique, you extract your particles from the flame. So this allows you to get particle size distributions. So you extract your particles from the flame, and then the terminology isn't something I really like, but you send those particles, like you extract your particles, and remember when you do when you take particles from a flame, the soot particles are actually charged. Some of them are charged, some of them are neutral, some of them are positively charged, some are negatively charged, and some are neutral. Okay, so when you take these particles out of the flame and then you send them through something called a neutralizer. And what the neutralizer does is it gives you a known or an assumed charge distribution. So it has a distribution of single charges, and you usually make this measurement assuming that you have all like single charged particles. It doesn't charge all of them. It charges some subset of them. So it's hard to get quantitative, but you can actually make some assumptions about how many particles are charged and see if you can, it gives you some kind of at least reproducibility. So you get this particle size distribution, and then the whole thing acts almost like a mass spectrometer for particles. So you have a single charge on a particle. The particles, and so it's a cylinder, so where you have a high voltage on, it's a coannular two cylinders, basically like electrodes. So you have a high voltage inner cylinder and then a neutral outer cylinder. And that puts a field inside the tube, and the particles drift through this field, right? So now you have a charge drifting through a field, right, electric field, and the particles are going to be diverted based on what the field they're experiencing, how big they are, and what their charge is, right? Their mass to charge ratio, basically. And you actually sweep the voltage on the inner rod, and particles of a particular size, as you sweep the voltage, respond to that field and go through, some of them, the ones that are in the sweet spot of that field, go through this hole at the bottom and then are extracted, and you count them. Usually count them with a condensation particle counter, which is just a laser. In order to count these particles, especially the small ones, you have to coat them with some kind of liquid, and there's usually like butanol. You coat the particles and then you can count them with this laser. And as you sweep the voltage, different particles of different sizes will go through, and then you count how many get through. That's what gives you the particle size distribution from a scanning mobility particle sizer. And this is a technique that like we use all the time. It's like been super, super helpful. So this is an example. Okay, so one thing to note about a scanning mobility particle sizer is that you can get multiple charges. So now, if you can actually use a part of this to select out a particle, like if you keep your voltage as single voltage, your inner rod is single voltage, you can select out one particle size. So if you want to do an experiment where you're just looking at one particle size, you send it through this thing and you just collect the particles that come out, okay? You say what size you want, particles come out. But your neutralizer actually gives you particles with 1 charge, 2 charge, and 3 charge normally. So when you send that distribution back through an SMPS, a different SMPS, you see 1 charge is the left, 2 charges the middle, because the larger mass has 2 charges and it thinks it's just 1 charge, so the mass to charge ratio is the same as the first peak. Same, and then you have 3 charges, and that's the distribution you get after you send it back through. Okay, so you just have to be aware of that when you're doing this. Okay, so that's dependent on the mobility diameter, right? The mobility diameter actually depends on, for soot, it's kind of confusing because if you had a spherical particle, the mobility diameter would be the same as that diameter. With soot, you have this like aggregate, right? This, big and floppy, and it's like, not spherical. So the mobility diameter is kind of confusing because this mobility diameter of a big floppy thing is going to be different from a mobility diameter of a spherical thing. And the reason is you're kind of drifting. It's an aerodynamic thing because you're drifting through this field, right, with a charge on yourself, and you go through, based on that, as you're drifting through, you're not under vacuum, you have a gas in there, and you're trying to make it through this gas with this force on you. Okay, so all that affects your how you get measured, but this aerosol particle mass analyzer or centrifugal particle mass analyzer is based on charge, is based on mass. So it doesn't matter how floppy you are, you have a mass, right? And this is kind of a cool, I don't know, I wish I had brought a picture of our CPMA. It's kind of this funky machine. It looks like it should be in an old cafe or something next to the jukebox. It's like it whirs and it spins, and what it is it has 2 cylinders, and one of the cylinders is spinning, and the particles are kind of like, whoa, want to fly out, like with the spinning cylinder, and you apply you do the same neutralizer thing, put a charge distribution, and then you apply this field to pull the particles back. So you're fighting this centrifugal force with this field, and that's how you use a centrifugal mass analyzer, and that is dependent on mass. So it's all really cool. And then you can compare. So a lot of people, when they're looking at soot, this is really common, especially for atmospheric scientists, when they're trying to understand how mature soot is or where it's come from, they want to do this measurement basically of how what is fractal dimension. Like we would put under a TM machine, right, and say, oh, okay, the fractal dimension is this. It looks like a regular aggregate from this. Hasn't been processed, blah, blah, blah. They'll often in the field take a mass measurement and a mobility measurement and compare them and say, okay, the mass measurement says this, but the mobility measurement it's not spherical, right? It doesn't give, so they have these relationships they've done with different particles of different shapes and masses and they have these correlations and stuff, and they tell something about, is this a diesel particle based on the mass to mobility ratio, which I find fascinating. Okay. And this is the aerodynamic aerosol classifier that does not actually even depend on charging. So this is kind of a new technique that doesn't depend on charging. Like you don't actually have to change, you just do it aerodynamically. You send the particles in aerodynamically, and then you still have the rotating cylinder, and you still have that centrifugal force, but everything's aerodynamic instead of by charge. By field, charge and field. So this is actually a really nice, you don't have to worry about single charges, double charges, triple charges. It's a really nice technique. I've never used one though, and I don't know how easy it is to use. The thing with a CPMA is it takes like, so in terms of time scale, if you've never used any of these techniques, like you can make a laser-based technique and whatever, you have 30 seconds. And average, whatever, you're doing 10 hertz, you can, average quite a bit in a few seconds. If you are using it CPMA, it might take 5 minutes to get one measurement. So it takes a long time for you to go through and make one of these measurements. I've never used one of these instruments. Okay. If you want to extract, this is a really cool technique that is an instrument that atmospheric scientists have been using for years, and is kind of the workhorse for measuring black carbon in the atmosphere, trying to understand how soot is emitted and distributed in the atmosphere to try to understand climate change. So people carry these instruments, out into the field. They fly them on airplanes, and it's kind of an interesting instrument because it measures soot using laser-induced incandescence, one particle at a time. But you have to extract your soot from the flame and send your soot through this instrument. So we haven't talked about laser-induced incandescence that much yet, but if you've ever used laser-induced incandescence, it's usually a pulsed laser, and it's usually a high-powered laser, enough to heat your soot up to a sublimation point of 4,000 Kelvin. So you really need a nice, big laser, and usually water-cooled and flash lamp-pumped YAGs. How they get the particles to high enough temperature with a tiny laser, they actually use just a small YAG laser. It's a CW laser. So instead of being pulsed, it just is continuous. So your particle, and the way they get the particle hot is in the middle of the laser cavity, they have this stream of particles. So you take your particle one at a time and let it go through your laser beam. It takes about 20 microseconds for your laser. Instead of nanoseconds, where you normally do these pulsed things like nanoseconds, this goes through microseconds, like 20 microseconds. So it is sitting there for a long time, just absorbing all of that IR and heating up, hopefully to the sublimation temperature, though it's not always true. And then it emits laser-induced incandescence, and you measure that single particle LAI. It's actually really clever. You also measure scatter from that single particle. So you can, then they have these fancy ways of comparing the timing of the LAI to the timing of the scatter to tell if your particles are coated and you're vaporizing. So they actually will do vaporization measurements. Like they say, okay, if I see scatter first and then LAI at a later time, I know it's taking me longer to heat up my particle, so I know there's a coating. And then they've done all these characterizations of this instrument to figure out what the coatings are. It's a really kind of fascinating technique. So you can then see the different, as a function of time, the different parts of your distribution, because you see one particle at a time instead of a whole distribution of particles. Okay. Oh yeah, and then one of the drawbacks of the instrument is the lower limit is about half of a femtogram, which is the particle size for soot particles about 140 nanometers mobility diameter. So if you work on diesel engines, that's a little bit too high of a lower limit to do a good job with diesel particles, because those particles are smaller. Okay, aerosol mass spec, that's another one we have to extract. Here's the instrument we use, and the typical mass spectrum we get. This is for particle composition. So we extract, and we send we'll talk about how we extract in a little bit. Send the particles, I think I described this yesterday, we send the particles through an aerodynamic lens system, which focuses the particles into a beam. It sucks away all the gas, so we don't see the gas phase. That beam of particles hits a plate, is vaporized under vacuum, and then we ionize using the VUV from synchrotron, and then do a mass spectrum. And then we can tune the photon energy and get our photoionization efficiency. And then, so this provides information about species that are on the surface that are vaporized, or species that are part of the particle that you can vaporize just by heating on the plate under vacuum. Okay, so here is a technique that's X-ray based, right? Where you're extracting, it's near-edge X-ray absorption spectroscopy or X-ray absorption spectroscopy. There are multiple different names that you can use. There are different ways of doing this technique, and you usually take your sample to a synchrotron and do these measurements. You can get, so basically you take your X-ray beam, and then you pull off an electron, right? And then you can actually either do the technique by looking at the electrons, or you can do the technique by, so what will happen? You pull off an electron, and you can either look at the fluorescence of, one of the electrons will fall back down into that hole, right? And you can look at that fluorescence. And when that second electron falls at the excited state, falls back into the hole you developed when you excited, another electron will fly off, and you can measure that electron, or you can measure the fluorescence. So there are two different ways of doing this technique, and you can get compositional effects, information about the SIP. And it usually, you'll have a peak that's related to graphite. So it's a pi to X star transition. So at that photon energy, where you have the transition from the ground state to the 1s to pi excited state, you can either look at that and try to understand about how graphitic your sample is. You can understand how many, the state over to the says 1s to sigma star. That's for these aliphatic, side chain type things. You can get information about oxygenated peaks, okay? And then XPS is also X-ray, and you basically hit the particle or your sample with an X-ray beam, and then look at the energy of the electron that comes off. So that gives you also almost like very, very similar information to NEXAFs, but it's very surface sensitive because you have to count on the electrons coming off, and if they're buried, your sample, if it's buried deep in the sample, you're not going to see those electrons coming off the surface. So that, what's hard about this technique, and probably also NEXAFs, is doing the analysis and trying to understand what you're seeing, because if you see there, like here's an example where you see this carbon binding energy. So this technique can give you information about, so that 284 is where you will get, it's called the carbon K edge. It's where you're going to get that excitation in carbon. What your carbon is bonded to, that the energy will change depending on what your carbon is bonded to. So you can get some information about the bonding to carbon to whatever oxygen, another carbon, whatever. But you notice how hard it is to see all those little peaks underneath that and then you're trying to fit all these little peaks. It can be really messy to try to analyze the data. Okay. Oh yeah, so this is really interesting. I haven't seen a lot from these experiments, but this is actually fascinating, where you do some of these X-ray techniques with a beam of like where you can extract from your flame and send. So I was just showing you techniques where you would sample by sticking a grid in the flame and extracting the sample and then carrying it over to the synchrotron and putting it at, putting it in an inert atmosphere while you get it over to your vacuum at the synchrotron and putting it in the machine and trying not to let it contact oxygen and stuff. This technique you actually can do online, so have a beam of particles that go into this machine and then on the fly in this beam actually do some of these measurements of X-ray absorption, or this one is for X-ray photoelectron, XPS, X-ray photoelectron spectroscopy, like I was just talking to you on the previous slide. So this is actually really interesting that you can do these measurements like on a beam of particles, and you can start to think, so this is an example of where you're almost merging a technique that's really hard to actually kind of sort out, right? Like do all the stuff to get to the machine, where you can almost start to exclude the surface from your particles are just going right from the sample into the machine. So you can start thinking about, okay, how about IR spectroscopy? Could you have a beam of particles and do IR spectroscopy on the fly? Could you do the same thing with Raman spectroscopy? So then you don't have to worry about the sample sitting on a substrate, or you can refresh your sample. You can actually continuously refresh your sample and maybe change something and do the measurement while you're changing something. So these are the types of things that we can start thinking about, right? Once you can do something like this and get rid of some of the complications, maybe there are other techniques we can do the same thing. And these would be types of things that you could do actually in your own lab rather than going to a synchrotron. So this one is also on the fly NextSAFs and XPS, where they make a beam of particles and then do the measurement as they're can change something, change the height in the flame or you're extracting. Okay, so here's some kind of a description of all the different types of spectroscopies, right? You have infrared, you're absorbing, right? Just direct absorption. You can do infrared overtone, like looking at multiple overtones of going from, say, the first vibrational state to, so the ground vibrational state to the first or the second or the third, so that would be overtone, IR overtone spectroscopy. You can do a spectroscopy where you get the same transition, but you do it by doing the Raman transition. So you excite and then relax back to that state and look at the difference in the photon energy. So that's another way. Instead of then you can do this type of spectroscopy. So basically getting the energy of a vibrational state you can do with actual visible light instead of IR light. So there are all these different ways to do spectroscopy, right? So when we talk about Stokes, that means that when you do the transition, you go up to an excited state and down. So you're going to a higher state, going to a low, going anti-Stokes. Yeah, going to a higher state, and then anti-Stokes is going to a lower state. Okay, so we're going to talk about Stokes and anti-Stokes in a little bit when we do cars. And then we can do different orders of Raman. So you'll see this, and the second order of Raman spectroscopy gives you more information, some other types of information related to the conjugation length in soot particles. I know this is like a lot of just dumping information at you. But this is like, you'll be able to look back and to go, okay, oh yeah. Do you have?
Yeah, the SM previously.
Oh, probably if I, let's go back to see, oh, let me see if I can do this. Hold on a second. Is this what you're talking about? Yeah, no, so the color, actually, it's color coded by temperature, which the experiment was done. So these were individual experiments measuring the particle size distribution as a function of temperature of the pyrolysis. Does that make sense?
Yeah, it was. I thought that it could be
Oh, yeah.
coupling it with
Yeah. Yeah, totally. So any of these techniques, and I think that there's a power in coupling techniques. So I would say instead of marrying yourself to one technique, even if, like, say your lab only does SMPS, okay, you're all here, and you're meeting other people who may have another technique. And if you collaborate, putting two techniques together can actually give you a powerful way of finding out new information. So I totally encourage you to talk to each other or talk to me. Like, I've done lots of different techniques. Maybe I could set you up with something at a synchrotron if you want to do a particular measurement you think that would help with your experiment. This is exactly, I definitely think it's worthwhile thinking about combining techniques. Yeah? Yeah, so keep meeting people, okay? Keep talking. Yeah, thank you. Okay. Okay. We're almost done with this part, I think. Okay, we talked about IR spectroscopy, right? And then Raman spectroscopy. Those are two ex situ techniques that maybe you could figure out a way to make them at least online. Maybe in situ, but that's awfully hard because you have luminosity from the flame. Okay, so that is a complicating factor. So remember, the G peak is your graphite peak. The D peak gives you information about, and Raman spectroscopy gives you information about defects. So you can use that technique to give you information about what's the fine structure of the particle. Okay, this technique is electron spin resonance or electron paramagnetic resonance spectroscopy. Gives you information about radicals. Like, okay, so can we find a technique that's like sensitive to radicals? Yes, this is it. But it has the big drawback is that you have to have a huge magnet to apply a big magnetic field, and then that magnetic field splits the energy related to that. Remember that you have this in a radical, you have a lone electron, it's either spin up or spin down, right? So depending on how your spin is aligned with your magnetic field, you're gonna have different energies of these states, okay? And you can do spectroscopy between these states, and this is what you can, so there would be two ways of doing this. You can either scan your magnetic field strength, right? Or you can scan the wavelength of your light. Your light is going to be probably terahertz, right? So your terahertz light, so it's 9 gigahertz, and you have a big magnetic field. So in this case, I think they keep the light the same, and they scan the magnetic field. And then they get a signal for their radical species. And as you notice, as a function of height in the flame, they get different signals for radicals. I'm not sure how selective this is without actually having a very fancy EPR machine. I haven't seen it because no one's done the experiment. So it tells you that about the radicals in the flame, but the particles in the flame, but I'm not sure how much you can get from this technique. Okay. Okay, NMR, nuclear magnetic resonance, similar to electron magnetic resonance, and now you're looking at the carbon. So this is a really, really, really common technique that organic chemists use. Again, you need a big magnetic field. In this case, though, you're looking at the hydrogens in your sample. So you can actually tell something about the bonding of the hydrogens to different carbon atoms. But it's and these are also huge machines, but you can usually have organic chemistry friends that can help you do NMR spectroscopy. And then we go to elemental analysis, one of the oldest techniques we have. But I think we need to do more elemental analysis where we can distinguish how many carbons, how many hydrogens, and maybe how many oxygens. And if you're doing something else, other elements that are involved in your particle formation. Okay, so I think this might be the last of the. Oh yeah, so this is also an ex situ. Remember, optical band gap gives you information about, let's see, the maturity of the particle. So this is where people have extracted particles and looked at the maturity using the optical band gap technique, trying to sort out how big are their species in the flame. Again, remember that's related to the how broadband your spectrum is, and the dispersion exponent. It's very similar. So it basically gives you the transition energy between your highest occupied molecular orbital and the lowest unoccupied molecular orbital. And then your dispersion exponent, we talked about that already. And then photoacoustic spectroscopy is kind of interesting. I don't know anyone in the field who uses it in combustion science, but I do know people use it in atmospheric science to look at soot particles in the atmosphere. Basically, it's you send a laser in, the particle absorbs, and then it does, it generates a pressure wave. As soon as it absorbs, it heats up quickly, it generates a pressure wave, and you put this into an acoustic cavity. You put your sample into the acoustic cavity, heat it, do this laser heating, and you look for the acoustic wave. It has some issues, like it's highly sensitive. You have to be very careful about the alignment of your acoustic cavity, but people do use it in atmospheric science. Oh yeah, so now let's look at, we're gonna come back to this because we're gonna look at an in situ version of this, but this is X-ray diffraction spectroscopy. Very, very old technique also, looking at the structure of materials. Anyone who does material science has probably come across this technique, where you basically look at the correlations between different, your X-ray beam hitting different surfaces in a crystal or different layers in a crystal, and then you have then they constructively or destructively interfere with each other. The beams, as if you think of the light as wavelength, and you'll get resonances at particular that are associated with particular spacings in your crystal. So you look at for those resonances, and let's see. Here's an example. And those can be associated with the layer. So for graphite, there would be layers in the graphite, right, between the different layers. But it's also, you can look at the spacings in the six-membered rings. Like you're going to have repeated structures in the six-membered rings. They're going to be constructively interfering to give you a peak. And different ways. So there are different resonances that are associated with the different ways that the beam can constructively interfere with different parts of your sample. Oh yeah, and here is Rosalind Franklin and one of her experiments looking at the X-ray crystallography or X-ray diffraction of this graphite sample. So, so here is a sample from a flame, and you can see the graphite peak. That's the 001 is the interlayer spacing, and then there's for soot. And this is one of the techniques that actually was very instrumental in telling us how far spaced the graphene sheets are in soot. So that gave us that answer, and it's been very consistent. Yeah, and then there's the 100 diffraction peak, which is commonly seen, and I think that's the spacing between in the plane, the six-membered rings. So it gives us information about the maturity of the particle. Okay, so let's quickly talk about sampling issues. Okay, so here are a whole bunch of, these are flames that we use in our lab. All of them give like different combustion conditions, right? And here's what happens when you put a probe in them. So you can see we actually do a lot of experiments where we probe the flame, and the probe perturbs the flame in different ways. Okay, and we use different types of probes depending on the type of flame that we have. And this is important not just for flames, it's also important for any reactive environment where you're trying to probe the particles you're generating. Okay, so this is one of the oldest techniques that people use for extracting soot from flames. It's where you take a grid and you it's like a rapid insertion, thermophoretic sampling, where you take a grid, you insert it into a flame really fast. So this rapid insertion, you have a pneumatic cylinder that like shoves that grid into the flame and pulls it back really fast. Or you shove it in, wait for a very short fraction of time to collect something and pull it back. But all of it happens really fast. You wouldn't be able to do it yourself. You have to have this pneumatic cylinder doing it. The grid tends to be on the order of like a couple to 3 millimeters when you're doing TEM grid sampling. So your sample can be pretty big compared to your flame. And people have found that it's better to have the grid vertical in the flame, but then you like mess up if you're interested in what's happening as a function of height in the flame and you have a 3 millimeter grid, you're gonna mess up your vertical resolution, right? So you inject this, and the grid is cold compared to the flame, so you are preferentially having the particles going towards your cold grid and sticking there, hopefully sticking there, right? And then you pull it out, and then you cool it off, and you put it in your TM machine, or whatever machine you're using. Okay, that's thermophoretic sampling. This is a tech, okay, I think this is, oh yeah, sorry. I made these slides a while ago when they needed them to print out like 3 months ago or something, or 2 months ago. So some of these I'm like, oh wait, I don't remember that. So yeah, this is another like where they stuck it into the flame, but they applied a voltage to it, and they think that this actually helps. And I would be interested to see what happens if you apply a positive voltage versus a negative voltage, because particles are going to be negatively or positively charged or neutral. So they collected, and they see more sample collected when they actually put a voltage on their sampling, their thermophoretic sampling system. I thought that was really interesting. So here's what happens. So here's the kind of the downside of this type of sampling is it can actually perturb the flame quite a bit. So it perturbs the flow field. Here are a couple multiple papers that have talked about how the sampling perturbs the flow field. This is perturbing the temperature, so this is a calculation of how the probe could perturb the temperature. And then this is like measurements of the temperature as a function of where the probe is inserted in the flame. So you see that, you know, there can be like a distribution of temperatures. So if you're inserting, so here's the question is, and this is true for all sampling, you stick the grid in. If you're cooling your flame a few millimeters from where you're sampling, you're actually changing the chemistry near where you're sampling. And I'm not sure what the effect is, but you also quench the radicals, so you're actually changing the chemistry around your sampling. So in this case, you know, I'm concerned. Like we do this thermophoric sampling, but I'm kind of concerned about this technique. So, and here are some, okay, so this technique, remember, is one of the first techniques. It's one of the most widely used technique for understanding what it looks like in a flame. This is how we've been sampling for decades, right? Using this thermophoretic sampling. So if it has some problems, is it affecting how we view the field? You know, what we know about soot formation. So that's just a question, I just don't know the answer to it. But it's something that we should be thinking about as a community. Like, are there different ways we can do this? Okay. This is another way to sample. You put a quartz probe or, you know, into, and remember, so here's what we want to do is like you want to extract the particles without perturbing your reaction, your system, right? You want to dilute them really quickly so they don't interact with each other, or with the gas phase, right? And you want to cool them really fast so that you quench all chemistry when you sample, right, as you get into your probe. So here are some attempts to do that. So you take a probe, and in this case, you have a jacket of nitrogen that flows around the probe, and then you suck into the probe, and the nitrogen goes up with the sample. So it's a very clever way of making a probe. The problem is the probe then gets bigger because you have this jacket of nitrogen around it. Here's another way of sampling through a tube with a hole in it, and you send nitrogen through. So this is like, it cools and dilutes in the tube as the particles go into the tube. You basically advect them into your hole in the tube and send them down. Both of these probes have been shown to possibly perturb the sample a little bit, like particle size distribution. And we found that if we use a metal tube and we get oxygen, like so if we use a co-flow diffusion flame and we're sucking from the flame, if we get a little bit, we get to closer to the tip, and we suck in some of the oxygen from the co-flow, everything's hot enough to catalyze, the tube gets really hot, the metal tube gets hot, and we catalyze reactions on the metal tube in the probe. Even though we've diluted, even though we've cooled a little bit, it still is hot enough to get oxidation of the sample in the tube. So we don't use this technique anymore with a metal tube because we're trying to understand the chemistry, and we get oxidation of the sample. Here's another way of probing. You stick a, you know, as talking about on the very, very beginning, you stick a quartz tube into the flame. We do this all the time. And then you suck out of the flame. So people have done, these are measurements showing the change to the temperature. So the probe is over there on the right-hand side. Let me see if I marked it. So the probe is on the right-hand side, and you see how it cools the whole region around the probe in the flame. That's really disturbing because that's basically cooling the whole region. You're really perturbing the chemistry. On the left-hand side, people have also shown that it really perturbs the radical concentration near the probe. So that's something that we have to worry about when we're doing this type of probing. I think I'll stop here, and because it's the end of our day, and you must be exhausted sitting here for so many hours. So go get some sleep, and I'll see you tomorrow, and we'll finish up the diagnostic section, then jump into atmospheric and have fun.